Welcome to the series of online lectures. Today we are going to have our first lecture, which is Interpolation and Polynomial Approximation. These lecture slides are prepared by using the Numerical Analysis by Burden and Ferris, 9th edition. And the topics we are going to cover in this lecture are why it's important to study numerical interpolation, application of the interpolation, and Weierstrass approximation theorem, polynomial approximations, and the Lagrange interpolation. I tried to make sure that for better understanding, there will be some small activities to perform. So make sure that you have some clipboard, pen, paper with you to perform those small activities. And then at the end of the lecture slides, we have some questions which are frequently asked questions. We will discuss about them as well. And at the end of the slides, we will have an assignment to help you and examine you that are you able to understand the ideas discussed in this lecture and how much you are able to understand them. So let's start with our formal lecture. So first of all, the question is that why should we study numerical interpolation and how it's important and why it's important. So as we all know that the fundamental laws of physics and the mathematics, they depend upon calculus, and the concept of function is a very, very foundational concept in calculus, and all the subsequent concepts are based on function like derivative, integration, partial derivatives, ordinary differential equations, and so on. So if we don't have a function, we can't take the derivative, we can't integrate, we can't solve an ordinary differential equation, and all those things. So that makes it a tricky situation if we don't have a function. So the importance of numerical interpolation is because we will learn to construct functions from data. Then there is an important question to ask ourselves. In the modern world, we see most of the times that the machine's output is in the form of a signal, or in some cases it is form of tabular data. So is it possible to express a signal in terms of a function or not? Like an ECG signal, no, it's a complex signal output. So what function can precisely express ECG is a question we should ask ourselves. And as we all know that the fundamental functions graph is not one of which match the ECG signal. So that third thing is that the machines generate information in the form of discrete data like tabular form or in the form of signals. So how can we link that discrete information and transform it into a continuous function? That is an important question again. And the last one is that in some cases, because machines usually generate data or fetch data in time periods, so it's very important to understand. In some cases, we need information in between a time period, in between two nodes, so which might be missing in our data. So that is a challenge for us to predict the value of the function at that point. So might take the help from interpolation to do that. Now to think how velocity is being measured by a digital meter in a hybrid car, we see that as we move to the electronics and more and more machinery output is being shown by LCDs and digital displays. So how do they work? The electronic speedometers, they usually measures the pulse that arrives by revolution of tire, and it converts it into a speed and displayed electronically on LCD like a circuit shown here. So let's say that the data fetched through the circuit is given in the tabular form. And in this table, we have a velocity versus time data, and we can see that as the time is increasing, the velocity is increasing, decreasing, and then increasing. So this means that the velocity is variable and it's a function of time. And so the important thing to ask myself is that I can see that the velocity is varying with respect to time, but I don't have any information about velocity at 7 seconds, 17 seconds, 23 seconds, and so on. So there are some points where I don't have the information, and I can't see any regular pattern to predict the value at 7, 17, or 23. So we will discuss later that how numerical interpolation is going to help us. So the question is, can we determine the velocity at 17 seconds? Obviously, I can't predict by looking at the velocity pattern from the data, and similarly the acceleration, which is a derivative of velocity at 17 seconds. Sorry. Now, the other thing is that I have a graph of an ECG signal, and these are two pulses. We can see that there are some peak node values and the depressions, and it's going up and down with an irregular pattern. So I should ask myself, do any kind of fundamental function like polynomial, exponential, trigonometric, or logarithmic is able to predict this graph? To me, certainly not directly, but maybe we can use some kind of combination to see whether we are able to do that or not. So now coming to how interpolation is going to help us to deal with problems that we usually face with numerical data. Interpolation is primarily used for two purposes. The first is developing a polynomial from the data set so that we can transform a discrete data into a continuous function. And the second is it helps us to calculate value at some missing nodes in the data. So we can use interpolation to calculate a value in between somewhere the nodes. Let's consider an example where a census is being done to calculate the population of the United States, and it's been done every 10 years. So the table shows the data of US populations back in 1950, 60, 70, up to 2000. And if we look at the data, we can't find some regular pattern in increase in population, and it's a discrete data. But on this data, a broader analysis is being done in economics, and policy decisions are being taken, like the food requirements, the infrastructure requirement, the hospital requirements, and all those things are related with this data. But unfortunately, this data is discrete. So this means that I need to plan for the population that will be in 1965. So in my 5 years plan, I should be able to at least guess the population value in 1965. But this data is not providing me the sufficient information to predict what is the value or what will be the value of population 1965 or similarly or in 2020. So it's very important to transform this discrete data into a continuous function so that we can predict the value at any year in between these data points. So we can use interpolation to predict the population 1975 or even in 2020. So we will later see how interpolation can help us to do that. As we know that usually machines generate and they store data in regular intervals. So in some cases, we have a missing value in between two data points, and we, for some reason, need to know that value. So we will take the help of interpolation to do that. Let's consider 2-3 examples where we can take the help from interpolation to do solve the problem. let's say we have some kind of machine which can store the position of any object at certain time intervals. So how can we take the help from interpolation to solve one of the few questions that I mentioned here? Like in a badminton match, we have the information about the shuttle position after each 0.1 second. Now this means that the machine is storing the position of shuttle after 0.1 second. So this means that if we require the value at 0.15, it's not available. So if it is integral multiple of 0.1, the information is being kept in the machine. But if it is not integral multiple, then we need to take help from interpolation. So let's say that we need to determine the position of the shuttle at 5.36 seconds, so which is not integral multiple of 0.1. So in this case, we have to take the help from interpolation to do that. Or like in a football match, can I exactly predict the time when the ball crossed the goal post line? Yes, definitely, I can do that. But for that, I should have some kind of information about football position, which might not be exactly available at the crossing line, but it should be around before the crossing line and after the crossing line. So I can join that information, do the interpolation, and calculate the time when it crossed the boundary goalpost line. Or similarly, in a cricket match, can I determine whether the ball bounced near the boundary is inside the rope or not? Definitely, I need to develop a polynomial for the height of the ball. And when a ball bounced at the boundary, this means that height should be equals to 0. So in this case, when the height is equals to 0, I can develop a polynomial, put it equal to 0, and then I can calculate that what was the time when it comes to 0, or what was value of the variable x when it comes to 0. So I can then analyze that information to determine whether it bounced inside the rope or not. So in all these problems, we can take the help from interpolation to solve. Now, have we ever think that if I have a discrete information about velocity, I'm going to take the derivative? Because in discrete form, we don't have some kind of function. Although from table, we can see that the velocity is the function of time and it's a variable. But for the case when we don't have a function, we can't take the derivative, because if we look at these constant values, we might predict that the acceleration is 0, which is not actually the case, because we can see that the velocity is varying. So there must be some kind of acceleration. So what is the acceleration at 17 seconds? A question for you. So definitely you will not be able to answer unless you learn interpolation or numerical differentiation to answer it. So interpolation can help us to determine the acceleration at 17 seconds, which we are not able to do right now. Now here is a small activity for you. Can you please write down some of the examples and think of that where you have a machine producing some kind of data and you need to do interpolation, or you might have done somewhere in your earlier courses, like in thermodynamics, you use tables to calculate the thermal coefficients or values of the thermal coefficient by using linear interpolation. So you might come up with some of the examples you already know about where you need interpolation to solve them. Now, formally starting with our lecture topic, that is that we want to express a function by a polynomial. So Wester's approximation sets the basics or foundation for the development of the concept of interpolation. So let's read what this theorem says. If we have a function which is defined on an interval a b and it's continuous, and there exists a small positive number epsilon such that the difference between an absolute difference between the function and the polynomial values on the whole interval are very, very small. So this means that if the difference between the polynomial value and the function value on each point of the interval is very, very small, then I can say that I can express this function by a polynomial. So will see that is in graphical form as. So in the graph, we can see that we have, let me get a laser pointers to discuss. So we have this blue graph, which is polynomial, and this black graph curve, which is representing the function. Now we can see that if we have a very, very small difference, so this curve is predicting the value of y, or the function f of x, in between these two dotted lines. So this means that we're not able to exactly predict this, but that is an acceptable range for us if epsilon is very, very small, like 10 raised to minus 3 or minus 2 or something. So up to certain decimal points, we have the accuracy. So polynomials, we all know that they are a combination of powers of x, so which are being represented in this form, which is an nth order polynomial, x raised to power n. So we will try to develop a polynomial from the given information, so that we can transform discrete data into a continuous function by means of polynomial. As we all know that it's not difficult, because we can express any kind of function in terms of polynomial by using Taylor series. So this means that we can express cos, sine, exponential, or any other function in terms of polynomial by using Taylor series, which is an infinite series. So let's discuss that how Taylor series is working to express any function in terms of a polynomial, and what's the issue with the Taylor series, that we need to develop some other techniques to do the approximation. Let's consider that we want to express a polynomial form of the exponential function e raised to power x by using a Taylor series expansion about 0. So if we consider only the first term of Taylor series expansion, it will be p naught is equals to 1. If we consider the first two terms, we have 1 plus x. If we consider 3, 1 plus x, x squared by 2. If we consider 4 and so on, considering 6 times, we have the p5 of x. As we all know that the Taylor series is an infinite series. So, but we can't take infinitely many terms. We always have to truncate it somewhere so that the result is acceptable to us. So we will discuss that in these 6 polynomials, p0 to p5, which one is more accurate. Graphically, if we look at the graph, the exponential graph and polynomial graph, we can see that the p0 is basically a straight line, is equals to 1. It matches the exact graph of exponential only at a one single point, that is 0. So this means that p0 is not a good approximation to the exponential function. So let's consider two terms, p1 of x. We can see that p1 of x is slightly better than p0 of x, but up to this limit, not greater than that. So still, it's not a good choice. Now, if we keep going with p2, p3, p4, we are seeing that they are coming close to the actual curve, and p5 is relatively much closer than any of the other graphs. But if we see after like 2 point something, like 2.3 or 2.2 something, we can see that these two graphs are moving away. Which means what? Which means that even by considering a fifth order polynomial, we are not able to come close to the exponential graph after 2.3. So this means what? This means that Taylor series is a good approximation to the exponential graph, but near 0. As we move away from the 0, even we are increasing the order of the Taylor polynomial, still their curves are not matching. This means that the error increases as we move away from the initial point 0. So we concluded that the Taylor series is a good way to express any function in a polynomial form but it's accurate near the point of expansion. And as we move away from the point of expansion, it's not that much accurate. So we need to now discuss something else to improve our polynomial approximation, so that it can match at 0, it can match at 1, it can match at 2, and it can match at 3. So the next technique that we are going to discuss will help us to improve the polynomial form of function, which is known as Lagrange interpolation. So let's consider that we have two data points, x0 and x1, and the function value is f of x0 and f of x1 at these two data points. Now at x is equals to x0, I want to develop a polynomial such that at x0 its outcome should be f of x0, and at x1 its output should be f of x1. So what I can do is I can write down polynomial as a linear combination of these two values, f of x0 and f of x1. So I need to multiply it with some variable coefficients which are known as Lagrange coefficients, L0 of x and L1 of x. Now I need to define these L0 and L1 of x in such a way that when I substitute x is equals to x0, it should only be f of x0. And at x is equals to x1, it should be f of x1. This means that when x is equals to x0, L0 of x should be 1, L1 should be 0. And at x is equals to x1, L0 should be 0 and L1 of x should be 1. Now, L0 is being defined as x minus x1 divided by x0 minus x1, because at x1 minus x1 will be 0. This means that at x1 L0 will be equals to 0. And at x0 minus x1 divided by x0 minus x1 will be equals to 0. This means that L0 will be equals to 1. So the strategy is that in the numerator, we are taking the differences such that at any other node other than x0, L0 numerator should be 0. And at x0, the numerator and denominator should be equal so that the comes equals to 1. So the same strategy is being adopted for L1. When we substitute x1, it will be x1 minus x0 divided by x1 minus x0 is equals to 1. And at x0, it will be x0 minus x0. So to repeat again, the strategy we have made is that L0x numerator should be 0 at all the nodes other than x0. And L1x numerator should be 0 at all the nodes other than x1. So we will keep in mind, we will use this strategy again to define Lagrange coefficients. Now, the result that we have already discussed is shown here, that L0 will be 1 at x0 and L1 at x0 will be 0. And similarly, L0 at x1 is 0 and L1 at x1 is equals to 1. Now, let's discuss an example to do a Lagrange interpolation for the two data points, which are 2, 4, and 5, 1. So in tabular form, I can express them as it. Now, by substituting the values of x0, which is chosen to be 4, and x1, which is, x0, which is chosen to be 2, and x1, which is chosen to be 5. In L0 of x, we will have x minus 5, which is x minus x1, divided by x0, 2 minus 5, x1. And L1, which is x minus x0, which is 2, and x1 minus x0, which is 5 minus 2. So we have the values of L0 of x, L1 of x. Now we need to do is substitute these values in the polynomial p of x, f of x0, and f of x1 values are given respectively as 4 and 1. So by substituting the values of L0, f of x0, L1, and f of x1, we have a polynomial which is minus x plus 6. So we can see that the polynomial that we are able to construct is a linear polynomial. And that's why it is known as the linear Lagrange interpolation. What do we mean by linear? We mean by linear is that actually in this form of interpolation, we express any set of data by a straight line. We can see that in a graph too. So this means that the polynomial we have established is a straight line joining these 2 points, and its slope is being calculated, and the equation of the line is y is equals to 6 minus x. So what if that these 2 data points are not part of the line, and rather than they are part of some kind of parabola, or might be they are part of some kind of circle? So then our approximation might not be good. So yeah, that's a problem with the linear interpolation. If the data is being dependent variable and independent variable are linearly connected, then it's fine. But if not, it's not the case, then our approximation might not be good. So let's move to 3 data points and see how it works. Now we have 3 data points, x0, x1, and x2, and we have the function values f of x0, f of x1, and f of x2. We want to make sure that our polynomial does satisfy this tabular data. So this means that our function or our polynomial should have the value f of x0 at x0, f of x1 at x1, and f of x2 at x2. So we use the same approach again, that we have written them as a linear combination of f of x0, f of x1, and f of x2. Now this time we have an additional Lagrange coefficient, which is L2 of it. Now the strategy will be the same again. We will try to define L0, L1, and L2 in such a way that we are able to transform this polynomial satisfying this tabular data. So let's start with L0 of x. Now we want to make sure that L0 x numerator should be 0 at x1 and x2. So I took the difference with x minus x1 and x minus x2 to make sure that at x1 and x2 L0 is equals to 0. But at x0 it should be 1. So to make sure, we need to divide with exactly the same terms. The only difference is we are going to replace x with x0, so that when we have in numerator x0 minus x1 and x0 minus x2, we can cancel out the numerator and denominator so that L0 can be equals to 1. So the same with L1, we want to make sure that L1 numerator is 0 at x0 and x2. So we took the difference with x0 and x2 to make sure that it follows the same pattern, and to make sure that L1 has a 1 value at x1, we took the same term in the denominator so that at x1 numerator and denominator should cancel out. So the same thing goes with for L2 of x. Now here is an other small activity for you. Can you quickly check does by substituting the values of L0, L1, and L2 in our polynomial p of x, can you quickly go through and check whether that our polynomial will satisfy the given data or not? I'm sure it will. And can you follow a pattern in Lagrange coefficient? Yes, I can follow a pattern, and we have already discussed that pattern, that the Lagrange coefficient corresponding to x0 at the node x0 should be 0 at all other nodes, and it should be 1 at x0. And the same goes for L1 and L2. Now, time to generalize that if we have more than 2, 3, 4, or generally we can say n number of data points or n plus 1 number of data points, so how we are going to define Lagrange polynomial? So let's consider that we have n plus 1 data points. As you can see, we are starting from 0 and n is the last one. So this means that 1 to n are n data points, and including 0, we have total n plus 1 data points. So when we have n plus 1 data points, we are going to do again the same strategy. Express the polynomial as a linear combination of f of x naught to f of x n, and each one being multiplied with a Lagrange coefficient. So here we can see an other variable which is mentioned as n. Actually, this shows the order of the polynomial. We will discuss that what does n shows here. So basically L0, L1 and Ln, the second index, it is Lagrange coefficient corresponding to x0, x1 and xn. And the first, we can see that the n is constant. This means that all of these Lagrange coefficients are of order n. So in a summation form, we can write down simply in the form of k0 to n with the variable k shown. Now, so to do generally define the Lagrange coefficient, we will adopt the same strategy we have discussed earlier, that we want to make sure the Lagrange coefficient at the given node corresponding to the given node should be have the one value when x is equals to xk, and it should be 0 for all other nodes. So generally Lagrange coefficient corresponding to a xk data point should be such that it should be 0 at x0, x1, so on, xk minus 1. It should not be x minus xk, because we don't want to make numerator 0 when x is equals to xk. So we skip xk difference. Sorry. And then we kept going x minus xk plus 1 to the last data point, which is x minus xn. Now we want to make sure that when x is equals to xk, the numerator and denominator should be same to make it equal to 1. So what we have done is substituted x with xk, which you can see that everywhere it is just similar to the numerator. The only difference is we have substituted x with xk to make sure that numerator and denominator terms cancel out each other when we substitute x is equals to xk. So our strategy works for each k 0 to n. Now let's try to apply the Lagrange interpolation for three polynomials. Sorry, not three polynomials, for three data points. I want to clarify one more point here about this n, the order of the Lagrange polynomial, or we should also say that Lagrange coefficient. The order of Lagrange coefficient and polynomial is same because we are adding them together. So we can see that all of Lagrange coefficients have the same order, that first 0th order Lagrange coefficient is of nth order, and the last one is also of nth order. So this means what? This means that actually if we look at, we have multiplied with x once, twice, so on till the last data point. This means that the order of Lagrange polynomial is generally the total number of data points less 1. Why? Because we have skipped 1, x minus xk. So this means that Lagrange coefficient order is being defined 0, 1 to k minus 1 to n. So we have first k minus 1 times x is being multiplied. So this is x raised to power k minus 1. We have skipped xk, and then we have xk plus 1 to xn. So this means that if you have 0 to n times, you have to multiply x 0 to n times, and you skipped one term. So this means that out of total n plus 1 nodes, I have skipped 1. This means that the nodes left in the numerator are n, and that what defines the order of the Lagrange polynomial, that it is an nth order polynomial. And one thing that we can also see is all these terms which are written as a sum, they are all of same order. So if first one is of nth order, the last one will also be of nth order. So let's discuss the example. We have three nodes at 2, 2.75 and at 4, and we want to perform a second order Lagrange interpolating polynomial for f of x is equals to 1 by x. So in this case, we have another example where we are already being given with a function. So this means that we know the function. Now we want to compare the result of a function and Lagrange interpolation. And definitely we know that this is not a linear graph. F of x is equals to 1 by x. Now second part, use this polynomial to approximate the value at 3 and determine whether it comes equals to 1 by 3 or not. So we'll check it later. So first of all, what I try to do is to fetch the values of f of x naught, f of x1, and f of x2 to make sure that I have the complete information in the data. So then I can calculate the Lagrange coefficients. So I took here L naught of x minus 2.75, x minus x1, and x minus x2. Definitely, we skipped x naught. And then in denominator, we have x naught minus x1, 2 minus 2 point. I think we found out some mistake, typing error here. It's not 2.5, it's actually 2.75. So sorry for doing it wrong. Okay, 2 minus 4 in the denominator, and finally we get this L naught of x. And similarly in L1 of x, we want to skip the node x1, so there will be no product of x minus x1 in the numerator. The rest is, we just need to substitute the value. Hopefully you can do it easily. And the last one is L2 of x on the similar pattern. Now, by substituting these values in the polynomial, we have 1 by 3 into x minus 2.75 into x minus 4 minus 64 by 165. Definitely we have multiplied L naught of x with f of x naught, L1 of x with f of x1, and L2 of x with f of x2. After multiplication, the final form we are getting is this. So we can see this is a second order polynomial. Now, if you connect it, what you have observed? We observed that the order of the polynomial is the similar to the last index value. So k is 0 to 2. So polynomial is of order 2. This means that the order of the Lagrange polynomial is usually 1 less than the total number of data points. So we have 3 data points and the Lagrange polynomial is of order 2. So the same goes for n number of data points or n plus 1 number of data points. Now, if we substitute x is equals to 1 by 3 in our polynomial, what we are getting is 0.32955. And as we all know that the 1 by 3 is a non-terminating fraction, goes 0.333333. So we can observe that we are coming close to 2 decimal points. So we are able to achieve some accuracy. And let's see graphically, and then we will discuss are we able to do better than the Taylor polynomial or not. So if we look at our data spread from 2 to 4, and blue graph represents the graph of 1 by x, and the black curve, it represents the graph of the function polynomial, Lagrange polynomial. Now, if we observe in our data range from 2 to 4, they are almost matching 100%, almost 100%. So we can see that that was not case for the Taylor polynomial. If we have done the expansion about 2, it would have been very good about 2, but it gets away from 3 onwards. That's not the case with Lagrange polynomial. As we can see that it's matching at 2, at 3, and at 4. So in Lagrange, we have forced our polynomial to come close to the actual curve at all the node values. So that's the outcome. We have seen that the Lagrange is better as compared to the Taylor expansion. Now, to think what we should think. The question is, will Taylor series expansion about x is equals to 1 match the actual curve 1 by x on the interval 2 to 4? So I have already discussed this answer, and I'm sure you got my point. Now, if there are 6 data points, what will be the order of Lagrange polynomial? Oh, not a tricky one. If we start with index value, we will allot the first data point 0 index, and the last data point index value will be 5. So definitely the order of Lagrange polynomial is 5. In very simple words, I can say the order of Lagrange polynomial is 1 less than number of data points, so it will be 5. Now, if there are n number of data points, what will be the order of Lagrange polynomial? I'm hopeful now you are able to answer this question. Now, what is the relation between the number of data points and Lagrange polynomial? I think the question is the same, just we are asking it another way. Is it possible to construct a third order Lagrange polynomial if 7 data points are given? And if possible, how? Okay, we want to construct a third order polynomial and we have 7 data points. This means that if we use all data points, the order of Lagrange polynomial will be 6, but we want only to be of order 3. Now this means that we need to reduce our number of data points. So we only need to take 4 data points out of these 7. By taking 4 data points, the order of a Lagrange polynomial will be 3. Yes, it's possible, but we need to analyze our data. I want to choose 4 out of 7. What is the criteria to shortlist those 4 data points? Remember, you need to choose 4 data points out of 7 which are in the surrounding of the missing value. Definitely you want to construct a polynomial to find some value at some node or at some point. So you need to select those 4 data points which are closer to the missing value and shed off the rest of 3 data points out of your data. So what you can do right now is write down, construct a table which have 7 data points, do it randomly, and then try to think that I want to calculate the value at this node or this point, and then shortlist 4 data points out of 7. I'm sure you will be able to do that. Is Lagrange applicable to equally spaced dataset or unequally spaced dataset? As we have seen that Lagrange has no requirement for equal spacing, so it's equally applicable to equally spaced dataset and unequally spaced dataset. So this means that Lagrange is not being affected by how data is being generated, whether it's equally spaced or not. Now, can we construct a second order or higher order Lagrange polynomial if we only have 2 data points? Sorry. Now it's your time to think. I have 2 data points. As per our understanding, the Lagrange polynomial order should be 1. I want to construct second or higher order Lagrange polynomial. So for second order Lagrange polynomial, I need 3 data points. But right now I got only 2. So this means that in this case, it's not possible. So what we conclude with is the limitation of the Lagrange polynomial is that we can reduce the order of Lagrange polynomial by reducing the number of data points. But if we have certain number of fixed data points, we cannot increase the order of Lagrange polynomial beyond the total number of data points. So I'm hopeful that I'm able to answer your questions. If you find some difficulty still, you can email me or we will have a live session to discuss. Now let's come to the last part of our lecture, an assignment, and we know that you need to practice and to make sure that you are able to grasp all the ideas discussed in this lecture. A sensor measures the position of a particle after a collision, and it's being maintained in a tabular form, which is shown here. Now we need to use Lagrange interpolation to estimate the value at 6. And we can see that in tabular data, we don't have the value at 6. So we are going to perform Lagrange interpolation to calculate the value at 6. So if we discuss, we have 1, 2, 3, 4, and this means that by using all these data points, I will be able to construct a third order Lagrange polynomial. And do remember one thing, the higher the order of Lagrange polynomial is, the better your solution is. So this means that I should consider all the points in this case, because I'm not limited to the choice to construct certain order polynomial. Moving to the next question, an engineer wants a projectile to pass through the given points. He decides to do this by using an interpolating polynomial p of x. So we have to calculate the y value corresponding to x is equals to 0.8. And we can see that again in tabular data, we don't have the information at 0.8. So we need to do Lagrange interpolation. We have 1, 2, 3 data points. So in this case, the order of Lagrange polynomial by using all data points should be 2. Third question, the acceleration function of moving drone is known to be a cubic function. Some values of the acceleration are given in table below. Find the value of A. So we can see that the value of acceleration is missing at 3, which is K. We want to calculate the value of acceleration at 3. Now, here is the issue. The issue is that we are given that the acceleration function of moving drone is a cubic function. This means that the order of the polynomial that we will construct should be of third order, because acceleration is a cubic function. Now, the data points we are given are 5. So to construct a third order polynomial, I should restrict myself to 4 data points. Now it's my choice to go for 1, 2, 3, 4 or 2, 3, 4 and 5, because it is equally spaced. If it would have been unequally spaced and then I have to restrict myself to 4 data points, I have chosen those 4 which are closer to the missing node value. So I should have gone for those 4 data points which will be close to t is equals to 3. So that is the strategy to select less number of data points out of the larger data set. Now the last question to discuss, in a badminton match, the shuttlecock strikes the ground near the border end. So by the way, it is the question from one of the past papers. The distance of the boundary from the center line is 22 feet, and it's a straight line distance, 22 feet. The horizontal distance covered by the shuttle versus the vertical height of the shuttle is given in the table below. By some means, we have the information about the height of the shuttle and the horizontal distance. After taking few bounces, the shuttle came to complete rest at the distance of 23 feet from the center line. Use the concept of interpolation to develop a second order polynomial to determine whether the shuttlecock strikes the ground within the code or outside the code. And even you have the choice to use calculator directly to solve the equation. Now, in this problem, we need to first of all analyze our problem, develop our mathematical strategy, and then solve it. To do that, what I grasp out of this question is that I need to solve by using interpolation. So out of this whole question, what I should concentrate on is the information required to solve by using interpolation. And that information is the relation between a horizontal distance and the vertical. And that is given in this table. Now, the second thing is, in the picture, I can see that a dot here. This means that the shuttle strikes somewhere near this line. So what I need to do, I need to develop a Lagrange polynomial. Now, when shuttle strikes the ground, this means that height should be equals to 0. So what I'm going to develop a Lagrange polynomial for the height of the shuttle, and then put that polynomial equals to 0 and solve to get the value of x. That is the horizontal distance from the center line. And if that distance comes out to be less than 22, the shuttle strikes inside the core. And if it's come greater than 22, shuttle strikes outside the core. So the strategy will be to develop a Lagrange polynomial for the height of the shuttle, put that polynomial equal to 0, solve it for x, and then analyze whether it strikes inside or outside. To do that, you should concentrate on one more point, that is develop a second order polynomial. Now the data points I'm given is 1, 2, 3, 4, 5, and 6. I need to develop second order polynomial, which means that I only need 3 data points. Now it's my choice to choose 3 data points. But I need to take those 3 data points which come close to where I want to solve this equation. And I know that it's the borderline near 22 feet. So I will choose those 3 data points which are close to 22. And from this tabular data, I can see that these data points are 18, 21, and 23. So I will take this, and this. Taking these 3 data points, I will develop a Lagrange polynomial, put it equal to 0, solve it for x, and then determine whether its value comes out to be less than 22 or greater than 22. If it's less than 22, shuttle strikes inside. And if it's greater than 22, shuttle strikes outside. So here, that's all from my side. We conclude our today's lecture here. I'm hopeful that you will perform these activities yourself and then do the assignment to make sure that you have grasped all the idea discussed in this lecture presentation. And so goodbye.